This meeting is being recorded.
In section 10 from chapter 7, we're introduced to some additional substrates rather, that can be used in addition to alkyl halides, such as these sulfonates. So we have these alternatives to our alkyl halides, and let's take a look at some of them that are shown here. So we have this first group that's called a alkyl mesylate that's formed. So this is the mesylate group here. This is a tosylate group shown here. And we have this triflate group shown here. All three of these substrates have very good leaving groups. So if you recall, the first step in a SN1 or E1 reaction is to have this leaving group and generation of a carbocation occur. Or with SN2 and E2 reactions, we have that concerted mechanism where the leaving group occurs as well. So having a good leaving group facilitates a more efficient reaction. So as mentioned, these sulfonates can be considered good leaving groups. They are very stable conjugate basis of strong acids that result. So we know that either due to inductive forces or resonance stabilization, all of these would be good leaving groups. And we're asked down here to determine, based on pKa value, which of these sulfonates would be the best leaving group. And we would look at the most acidic compound here and find that its conjugate base would be the most stable. So this TFOH, this trifluoromethane sulfonic acid, and the resultant TFO group that is used is considered the best leaving group of these three. So let's look at how sulfonates can be made from a corresponding alcohol. So we have this alcohol here, and we treat it with what's called tosyl chloride. So we have this chloride attached to this tosylate group here. And what happens is we react our compound with pyridine, and after this first reaction occurs, the pyridine can deprotonate the alcohol, and we end up with this structure here, this alkyl tosylate. And we should note that alcohols, when they are turned into tosylates, we do not change our configuration. So there's no inversion of configuration when we prepare a tosylate, and overall, nothing is changed besides this hydrogen is now replaced with that TS group. So no change in configuration, but when we have our SN1 reaction occur, we would see an inversion of configuration. So now that we have our tosylates, we see a primary tosylate here or a secondary tosylate. Either of these can be treated with a strong nucleophile, strong base, such as hydroxide, and we would see a mix of products. So for this first reaction mechanism, we would see a mix of our major product, our substitution product, and then a minor elimination product. Then with our secondary tosylate, shown down in the second row here, we treat that with the same reagent, the strong nucleophile, strong base, the hydroxide. And now we'll see that with a secondary substrate, our major product will be an elimination product, and our minor product is now the substitution product. So again, you should begin to look at the substrate to determine what reaction mechanism will be your main mechanism, whether it's elimination or substitution, as we see with these cases here. So alcohols can also be used in substitution and elimination reactions, similarly to the tosylates that we saw. And what we see here is a primary alcohol. We can treat it with an alkyl halide, or with this hydrobromic acid, and produce an alkyl halide. In this case, it's a primary alcohol, so we would produce that primary bromide as our product. And of course, water as well, right? The OH and the H form our other product. So we would need strongly acidic conditions in order to accomplish this, because H2O is, I'm sorry, OH is not a good leaving group, but if we use something like hydrobromic acid to protonate the alcohol, we can see here that water is a much better leaving group, and that leaves the bromide ion available for a nucleophilic attack at this site here, and then that forces this water molecule to be ejected, and by that path, we have our SN2 mechanism and our alkyl halide product produced. So alcohols can participate in either SN2 or SN1, depending on what type of substrate. So we see that primary alcohols are going to follow SN2, but secondary and tertiary alcohols will follow an SN1 pathway. So that's what we see here. We see this tertiary alcohol. We see that we are going to generate a carbocation intermediate in this second step here. So first step, we protonate our alcohol, we generate this species here. Then we see that water molecule is ejected as a leaving group, and then we have our carbocation generated here. And then that nucleophilic attack happens in this step here, and we generate that tertiary bromide. So we reviewed different solvents can affect reactions, and we know that strongly acidic conditions are protic conditions, which would favor SN1. But since we know that these primary carbocations are too stable to form, primary alcohols would then react via the SN2 mechanism instead. They're unable to stay in that carbocation in the primary state, so therefore they follow that SN2 mechanism. So then we look at alcohols and elimination reactions. Alcohols will undergo E2 elimination if we use the strong acid here, sulfuric acid. So concentrated sulfuric and heat are the driving force of this reaction to take a tertiary alcohol and cause an elimination to occur, and we generate this alkene and, of course, water as a byproduct. So once again, we have these strongly acidic conditions. These are protic conditions. Our solvent is a polar protic solvent, and therefore E1 would favor for secondary and tertiary substrates. So we have that tertiary alcohol shown here. We have our first step in the mechanism, a proton transfer. Here's our acid source, right? This hydronium ion shown. Then we have our, in step 2, loss of leaving group. And remember, if we have a neutral leaving group, we will have to have a third step here in our mechanism for a subsequent proton transfer to create our final product. So we'll take a look at synthesis in our next video.